will take a look at is the cotangent of the inverse sine of x. So the goal here is to eliminate all the trig, and when we're done, just have an algebraic formula. Do either one of you remember which trig function you usually start with, the outer or the inner? Yep, I'm going to start with the inner trig function. Now, whenever you use inverse sine, you're always trying to calculate the what?
Angle.
Yeah, you're always trying to find the angle. So the inverse sine of x is going to equal an angle. I don't know what angle that's going to be, but I'm going to represent it as a Greek letter. All right. Now, we want to try to draw a right triangle diagram, but I need to rewrite this using regular trig. So what can I do on both sides that would get rid of inverse sine and make it regular sine? Yeah.
Take the sine.
Yeah, take the sine of both sides. So take the sine of what's on the left. Do it on the right. The inverse and regular sine cancel. And now we get x equals sine theta. We're going to want to think of that x as a fraction though. So how can I make x a fraction? Yeah,
X over 1.
yeah, let's just put it over 1. And now we can draw a right triangle diagram. So put theta in the diagram. It just has to be one of the acute angles. And they're giving me the sine. When you know sine, what two sides in a triangle is sine? It's the what over the what?
Opposite over hypotenuse.
Opposite over hypotenuse. So opposite is x, and the hypotenuse is 1. Now we've drawn a diagram for what I put that black box around. Now they want us to find the cotangent of the black box, which is our picture. What is cotangent?
Adjacent over hypotenuse.
Cotangent is not adjacent over hypotenuse.
It's 1 over 10.
It's the reciprocal of tangent, which is...
Adjacent over hypotenuse. Well, that's...
No, that's what you said the first time. So tangent is what I'm thinking in terms of the names of the sides, like the positions. It's the what side over the what side.
Opposite over adjacent.
Opposite over adjacent is the tangent. We're looking for the cotangent.
Adjacent over.
Adjacent over opposite. So I need this side over x. We're not going to be able to figure that out until we figure out what this side is. I have the other two sides, x and 1. So how can I write an expression for the third side? Yeah, use Pythagorean theorem. So x squared plus a squared equals 1 squared. And when we solve for a, what would be my first step?
Subtract x squared from both sides.
Yeah, I'm going to subtract x squared from both sides. And my last step. Yep, take the square root off both sides. Alright, so now I don't have to use a anymore. I have a formula. It's the square root of 1 minus x squared. And what are we finding? Cotangent. So formula for cotangent was adjacent over hypotenuse. Okay, so what side is adjacent here? Yeah.
Square root of 1 minus x squared.
Square root of 1 minus x squared. And what's the hypotenuse?
1.
I'm sorry, adjacent over opposite.
Okay.
Square root of 1 minus x squared over
X.
x. Yep. And that's the formula. That should be the formula for the cotangent of the inverse sine. You can double check it by putting what's on the left in y1. And actually, we can just make sure we did it right. So cotangent, that is 1 divided by tangent. And it's the cotangent of the inverse sine. second inverse sine of x. Okay, so we got that in y1. Let's put the square root of 1 minus x squared. X. Let's get rid of those. 1 minus x squared divided by x. If we did it right, we go to our table. Y1 and y2, the values should be exactly the same. So let's go here. Right, so we got to pick a value that we can plug in. You can't go above 1 or below -1. Otherwise, you're going to be taking the square root of a negative number. So you can pick a number like 0.8. Okay, looks good. Those are the same. Let's just try another one, 0.6. And we'll do -0.7. Perfect. They look like they're the same. So that's how you convert a trig formula into an algebraic formula. Any question on that? Okay, so next question we're going to look at is solving an equation. Let's solve it from 0 to 2 pi. We'll write those answers. And then we'll look at how would you do it if they wanted all solutions instead of just 0 to 2 pi. So 0 to 2 pi, this tells us our window. Okay, so that means we're going to look at the x min. We're going to set that to 0, and we're going to set the x max to 2 pi. Now, sine squared is going to be between 0 and 1. But tangent has a vertical asymptote in it. That's going to cause the graph to go up and down forever, okay, because you have that tangent. If you didn't have the tangent here, this would be a no solution. Sine squared never equals 2. Doesn't go that high. All right, so remember, when you type it in, you cannot type it in the way it looks on paper. You have to type in sine squared, just like I have it in y1. All right, so put the left side in y1, put the right side in y2. We've already got our window set, so we hit graph. And how many times in that interval does it look like they cross? Yeah, looks like they cross twice. So we do second calc intersect. Okay, I'm going to do the one on the left and just see what we get. So we get 2.21. That would be one answer. And then second calc intersect. Got to keep moving your cursor till you get onto that other part of the graph. That should be good. And we get 5.35. Okay, so those are your two answers from 0 to 2 pi. Any question how to get the answers in that interval? All right. Now, let's say they wanted all solutions. If they want all solutions, the first thing you have to do is find the least common multiple of all periods. What's the period of sine squared?
Would be 4 pi? Or
No, it's not 4 pi. It's sine to an even power.
just 2 pi?
Sine to an odd power is 2 pi. Different formula for sine to an even. Yeah, it's pi over b. Okay, sine to an even power is pi over b, and in this case, b is 1. So the formula is pi over 1. So the period here is pi. What's the period of tangent? That's also pi. So what's the least common multiple of pi and pi? Pi. So if they ask you for all solutions, that's the first step, and that tells you what to set your window to. Because you only want to find the solutions in one cycle. What we actually did in the last problem, we found the same answer in 2 different cycles. This answer is a repeat of that one. That's what they wanted, so that's what we did. But when you're doing all solutions, you don't want to list repeats. So to avoid repeats, set your window to 1 cycle. Hit graph. You're going to find the intersection, which we already know. It's going to be the first one, 2.21. So is there any question on how we got the 2.21? Okay. So now you write that one down. And now you tell me, or you put something on the end to indicate that that solution repeats forever. What would you put on the end of that to indicate that that solution is going to occur later on? Yeah? Yes. So if you were to add 3.14 to 2.21, you would get 5.34. And if you were to add 2 pi again, you get the next answer. So this is how you write all solutions. Question on the difference between the two?
Can I just see what you put in for y1 on the graph?
For the y1?
Yeah.
Yep. So that's how you put it in. Sine squared x minus tan x. Yes.
How do you remember like what the periods are for each one? I know like odds and evens depend on it, but like what's a good way to remember it?
Well, if you can remember one of them, then you can automatically remember the other one because it's not the one you remember. So, because there's only 2 cases. So I would say if you can remember, like, if you have, let's see, which one's the shorter one to remember? I would say sine. I think the shorter one to remember would be if you have sine to an even, cosine to an even, secant to an even, or cosecant to an even. The period is always pi over b. So if you can remember that these 4 are pi over b, then everything else is 2 pi over b. So that would include sine to an odd, cosine to an odd, secant to an odd, cosecant to an odd, or any tangent, even or odd. So I just remembered this. And then everything else is 2 pi over b. So yeah. So these are all pi over b. And mess that up. So tangent to an even or odd is also pi over b, and cotangent to an even or odd. So those are all pi over b. So that's actually the long one. I wanted to put up the short one. So sine to an odd, cosine to an odd, secant to an odd, or cosecant to an odd. That is 2 pi over b. So that covers everything now. So I remember the shorter one, which is the bottom. Sine, cosine, secant, and cosecant to an odd is 2 pi over b. Okay, so any questions on which one are pi over b and 2 pi over b? That's right. All right, so let's simplify this trig expression. So it's tangent times cosine. I wouldn't be thinking about common denominators because you don't have any fractions. I also wouldn't even think about conjugates because you don't have like 1 plus a trig function or 1 minus a trig function. So there's really only one trick left that I explained in class. So what might you want to try first? Yeah?
Change tangent to, is it sine over cosine?
Yeah, so change tangent to sine over cosine. And since we made that a fraction, might as well make cosine a fraction. And what's going to happen when you multiply those together? Yeah, what will cancel?
The cosines.
The cosines. And what are you left with?
Sine.
Sine. So the tangent of an angle times the cosine of the angle is the same as just taking the sine of the angle. That's it. Any question on that one? Okay. Okay, so here's another simplify. And is there anything here that you might think about doing first? Yeah?
There's a conjugate.
Okay, so we do have 1 plus tangent squared. You might want to think about like maybe doing something with 1 minus tangent squared. Anything else?
Changing it to sine and cosine, but I feel like the other way better.
Okay, so we could try changing everything to sines and cosines. That generally will always work, but it tends to probably be the longest way to do it. Sometimes it could be the shortest, but it's usually like a longer way to do it. See, we notice anything else there? Looking at what we have.
Negative squared.
What is it?
Negative squared.
Okay, there's something squared. How about the top?
Oh, is it identity?
The top is an identity. Right? If you look at identities, there's even more identities here than what we did in class. But look for 1 plus tangent squared. What does it say over here?
Secant squares.
Yeah. Get bigger. 1 plus tangent squared is secant squared. So let's try that right away and just see what happens. Okay, so now we have secant squared divided by cosecant squared. Now I would say let's try changing to sines and cosines and see what happens. But pretend the squared isn't there. What is secant? It's 1 over what?
Cosine?
It's 1 over cosine. So what do you think secant squared is?
1 over cosine squared.
1 over cosine squared. All right. How about cosecant? What's just regular cosecant?
1 over sine.
That's 1 over sine. So how about cosecant squared?
1 over sine.
1 over sine squared. Okay. And now we've got a fraction divided by a fraction. What do we do to divide two fractions?
Multiply by the reciprocal.
Multiply by the reciprocal. So we have 1 over cosine squared times sine squared over 1. What's 1 times sine squared? Sine squared. And what's cosine squared times 1?
Cosine squared.
Cosine squared. Now, this isn't exactly one of the ones we have over there, but it's close. Do you see what sine squared over cosine squared is close to?
Tangent.
Yeah, it's close to tangent, right? Sine over cosine is tangent. So what do you think sine squared over cosine squared is?
Tangent squared.
Tangent squared. And that's the answer. Right. So let's just make this whole page again. So if you started with 1 plus tangent squared over cosecant squared, that entire thing turns into just tangent squared. Any question on that one? And there might be other ways to do it. I don't know if that was the best way. I mean, that was really, I would say 1, and then 2, 3, 4 steps. About 4 steps. Certainly not that bad. All right, so this one, it's asking us to evaluate an expression. So it says inverse cosine of 0.63. Is 0.63 a number that you recognize from the unit circle? Numbers from the unit circle would be like 1, -1, 0, half, root 3 over 2, root 2 over 2. So this isn't going to come out nice. So we're just going to find the answer in degrees and radians. Okay, I am in radians, so let's do that one first. How do you type in inverse cosine 0.63?
Second cosine.
Second, cosine,
0.
and then 0.68. Okay, so that's the answer in radians. And if you didn't have a degree button, you could change it manually, but we have a degree mode, so just change to degrees and type the same thing in again. Okay, and I'm going to put a little circle on that one so we know that that one was degrees. So, any questions on how we get those? Now, let's say we had one that was a number that we should recognize from the unit circle. The inverse sine of, let's see, root 3 over 2. Okay. And let's say I ask you to do this one as an exact answer. In radians. Well, if you go to radians and you type in inverse sine square root 3 over 2, and you write down 1.047, is that an exact answer? No, that's a decimal. So I tell you that I'd like an exact answer. What mode should you do it in first?
Degrees.
Yeah, let's do it in degrees first, because it will come out nice. So we'll switch to degrees. Do the inverse sine of square root 3 over 2, and we get 60 degrees. Now, is that exact? 60 degrees? Yes. Now, I did ask for it in radians, so how do you convert degrees to radians? Yeah?
Multiply by pi over me.
Pi over me. And what would you get for a fraction when you reduce that? Pi over 3. Now, if we want, we can check pi divided by 3, and we already know it should come out to 1.047. Yep, 1.047. So that's how you get the exact answer, if that's what they ask for. Any question on that? All right, so last question is finding the domain and range of an inverse trig function. The way you figure out domain and range is you have to know what it would be originally. So let's write it down for inverse cosine. So this is the original. What's the original domain for inverse cosine? If you can't think of the original domain, then think of the range of regular cosine. What's the range of regular cosine? Yep.
-1 to 1.
Yep. -1 to 1. Remember, the range of regular cosine is the domain of inverse cosine. Okay. Now, how about the range of inverse cosine? Think of the domain of regular cosine. We had to limit it to pass the horizontal line test.
Would be negative pi over 2 to pi over 2.
That's what we did for inverse sine. But that doesn't work for inverse cosine. Anyone remember what we had to limit the domain of regular cosine to? Anybody have? So we did negative pi over 2 to pi over 2 for, we actually did that for inverse sine and inverse tangent. There's only one other one we had. Not negative pi to pi. Closer, something with pi. It begins with a z and ends with an arrow. Does anyone remember?
0 to pi.
Yeah, 0 to pi. So the range on this is 0 to pi. So you want to make sure that you know the domain and range of inverse sine, cosine, and tangent. Okay, that's important.
Can you write those?
Yep. So inverse sine. The domain is also negative 1 to 1, because that's the range of the regular sine, negative 1 to 1. And the domain of regular sine, we limited to be negative pi over 2, pi over 2. So the domain of regular sine becomes the range of inverse sine. Okay, so sine and cosine are similar in terms of their domain and ranges. But inverse tangent, that one's a little different. Do you remember what the domain is for inverse tangent? Yeah. All real numbers. Inverse tangent looks kind of like this. It goes left and right forever. So domain is all reals, but it doesn't go up and down forever. There were horizontal asymptotes. Where are the horizontal asymptotes for inverse tangent?
Is it -1?
Negative what?
-1.
It would be where the vertical asymptotes are for regular tangent. So whatever the verticals are for regular, they become the horizontals in the inverse. Not pi.
Is it negative pi over 2 to pi over 2?
Negative pi over 2 and pi over 2.
What would we do with the negative side?
Okay, subtle difference though on the range between inverse tangent and inverse sine. One has brackets, one has parentheses. So that's important. All right, so now let's see if we can find the new domain and range for this one. All right, so let's start with the domain. What number there is going to affect the domain? The 3 or the 2?
The 2.
The 2, right? So the way we did it is I said to put the argument in the middle and then put the original domain on the left and the right. What's the original domain for inverse cosine?
-1 to 1.
Negative 1 to 1. So now if you solve for x, the new domain is basically cut in half. That 2 is causing it to compress by 2. So what would be your new domain using interval notation?
-1/2.
Yep.
Is less than
No, if you put a less than or equal, that's an inequality. So we want to write it as an interval.
So, -1/2 to 1/2.
Yeah, so -1/2 to 1/2. Okay, so there's the new domain. And what number here is affecting the range?
The 3.
The 3. What's the 3? What kind of transformation?
Vertical stretch.
Vertical stretch by how much? Factor of 3. So if you take the range that you started with and you stretch it 3 times as much, what would it become?
0 to 3.
It would become 0 to 3 pi. And that's how you find the domain and range of an inverse trig function. Okay, all depends on the original. You really got to know that. Okay, any questions on that one?